we'll figure it out as we go.
Sounds good. Welcome, everybody.
Is this going to be recorded?
It is. There's a problem though. In I don't know why, but on my Discord screen, like everything shows up backwards. So if I write something here, it like this says gnihitemos on my screen, including what I'm recording. So I don't know how that's gonna work.
Oh.
Yeah, I know it looks fine for you, but like the OBS
always
screen
reflect in
captures. Yeah, I could, but then the chat is also reflected in post. So I don't
Put a
know.
mirror with you? Just look through a mirror.
Complicated editing.
Yeah, or just write backwards. No.
Can't you use the Craig thing that you used last time to record the view that others see?
That only records audio. That has nothing to do with the video streams.
Oh.
Yeah. Anyway, I'm just gonna go with it. I'll figure something out, maybe. Anyway, welcome everyone. I'm curious, just as a show of hands or voices, how many of you have not solved a Rubik's Cube?
Yep, I haven't ever.
Ooh, okay, we got one. Anyone else?
I haven't solved it in like a decade or something.
Okay, that's good. Has anyone, well, let's say, in addition to that, has anyone not invented their own solution to some kind of Rubik's Cube-like puzzle, such as this? Just any twisty puzzle that involves permutations of objects. Yeah.
I have not invented a solution to any twisty puzzle.
Okay, sweet. So that's basically the goal today, I think. So just to start with some like the basics, these things are groups, right? So the elements of this group are going to be the permutations of all of these pieces. And when I say pieces, I mean the physical mechanical pieces. You can also think about it as like permutations of stickers as well, but you can it's kind of interchangeable. Depending on the context, it makes more sense to think about stickers as being permuted with each other versus pieces being like permuted and oriented. But in either case, the idea is that I can do some operation on this cube, whether that is like just some sequence of moves or just one turn or what. That is an element in the group that we're concerned with. So we have some group, and for each state of the cube, you can think of it either as the group element being that position or the operation that gets you to that position. I'm going to suggest you think of it as the latter. Think of a group element here as the action that transforms the cube, because that way you can just think of the composition operator on our group of like doing how do we add two group elements? The answer to that question is just like do one and then do the second one. So like if we in the notation of the Rubik's Cube, you don't need to know what this means, but like our group operator of like addition adds two things together by literally doing R, meaning a right turn and then an upturn. So that is how you compose two elements in the group. Does that make sense?
I assume these are non-commutative, right?
Yeah, okay, perfect. That's exactly what I was about to say next. So the Rubik's Cube is not commutative. We can prove that just by like looking only at this face. I'm going to do R then U, and now you have like 3 green on the top and then red, red, white, red, red, white. And then if we do UR, we have 2 greens on the top and then 1. So that's proof enough right there that it's not a commutative group. You add 2 things, you get two different consequences. Does that make sense? Anyone not following so far? I'm not going to prove that this is a group, but what you need to know here is that there are operations and you can compose them. That's the important thing to take away. So
are we going to stick with this notation where it's the opposite of the order of function composition?
I'm probably not even going to really use notation much at all. But yeah, we'll see. I don't know. I'll cross that bridge if I come to it.
The plus is a little weird because plus implies commutative group. So
Uh,
FYI.
what are you suggesting? R dot U?
Maybe
what
an
is the
arrow, implying an order.
arrow? I guess you could do an arrow. That could be our group operator. Um, like
if you want
comp,
R,
we
then
could do like
U, then
composition
arrow is better than
composition
standard.
O.
Because composition
Composition
order.
But
is
that's
the
yeah,
reverse
yeah.
order
This is
standard,
reverse
like
order,
it's
right? Yeah. But I don't intend to talk much about notation anyway, so forget about that. The only notation that we're going to probably ever mention in this talk is what a commutator actually is. So I'll just go ahead and define that right now. Like a commutator, it's usually written like this. If you have a commutator of x and y, I think it's usually written like this. And I don't actually remember the order, but the idea is that you do one of the elements, you do the other element, you do the first thing backwards. This is like the inverse, so you can say -1 x to the -1 for the inverse, and y to the -1 for the inverse of y. So this might be like y comma x. I don't remember exactly which order that it is. I think the inverses come first in reality. But the idea is we're doing something, doing another thing, undoing the first thing, and then undoing the second thing. So a question that you might ask immediately is, why is this even called a commutator in the first place? Well, it has to do with commutativity. So as we said, this group is not commutative. If you do two things, it depends on what order you do them. That will determine what you get as a result of doing the two things. However, in a group such as like addition, like 5 plus 3 plus -5 plus -3, like this is a commutative group because like we can swap things around, but being able to swap things around implies that the commutator is the identity of the group. The reason for that is we can like just swap the two things on the inside of the group, and you'll get like x inverse, y, y inverse, and obviously these two cancel out, and you just get the identity. So this is kind of the magic trick to inventing your own solution to puzzles like this. And the reason is, if you can get x and y to sort of almost commute with each other, then you can make very surgical operations on just a few pieces. So what I mean by that is like, on the Rubik's Cube, we'll talk about a couple of different examples, but like, actually maybe I'll start with addition. So since addition is commutative, you get the identity. If we take two operations on the Rubik's Cube, like this, that don't have any overlap, and then you like construct a commutator out of them, that is to say the right face, the left face, undo the right face, then undo the left face, you have, those commute with each other, so you get a no-op, you get nothing that happens. However, if you do two things that do not commute with each other, if you have two sets of pieces that are changed in your x and in your y that have an intersection, like for example when I do this, the commutator is now not the identity. I've done something to the cube. Does that make sense? So I'll take that as a yes. So the idea here now is, if we want to do some kind of small operation on this cube, the way to do it is pick two actions that have a small overlap. Now, in terms of actions, I've written this as like x, y, x prime, y prime, where it looks like x and y are just like single turns, but they don't have to be. We can compose turns together to construct our x and do the same for y. So just from what I did there alone, this is the sequence that I did a couple times now, you'll notice that like the set of pieces that is changed here is like this set that comes all the way into the back. It's kind of like a little snaky path here. So this is the set of pieces that changes. Now, you'll notice that on the left side, there's only one piece that has not maintained its original place. This piece here. In other words, if our x is equal to this thing, this first commutator, or sorry, this first, yeah, well, it was a commutator. we're making our x now a commutator, so this is going to be a nested commutator. Then we can make our y be just turning the left face. Then we undo our x, and then we undo our y. You end up with like just a few things changing. So that is sort of the magic and the point of why we do commutators, is you can make very surgical and specific operations if you select these two things to only barely not commute with each other. Does that make sense?
Well, I guess the goal makes sense, but I don't understand
That
how
was
we would.
almost magic to
that.
me, seeing how it just resulted in 3 pieces
Yeah.
rotated with each other.
Yeah. So, sorry, what did you say, Dirib? By the way, am I pronouncing that right? Is it Dirib?
Doesn't matter.
Okay. So, what was your concern?
What I said was like, I understand the goal of it would be nice to have operations that don't change much of the cube, and I
Yeah.
believe that some commutators could be that, but you made it sound like just pick x and y so that the commutator will come out to not do much, and I don't know how to do that.
The way to make the commutator come out to not do much is like physically assessing the amount of pieces. Like you can imagine sort of like when I do this, we're actually watching the amount of like the set of pieces that change. Think of this cube in like in your head. Picture this cube in black and white, where like all of these pieces have not changed their position. Like all of these pieces have also not changed their position. These are the ones that have. And like think of the set of pieces as a set, and then think of the set of pieces that change here as just a different set, which is just the set of pieces on the left face of the cube. So the intersection of those two sets is what we're concerned with. In this case, it was literally just this one piece. There was nothing else that, there was nothing else that was in both sets except for this one piece. Because the intersection of the two operations, the pieces that are changed by the two operations, because the intersection of those sets is 1, you get this very small, this small action.
Okay. I mean, I don't know why that would be true, but it sounds helpful.
Well, let's watch what happens. So, I'm actually going to take a simpler puzzle as an example. So, this is a puzzle that just turns on its corners like this. Our commutator here will be very simple. We're going to do like a turn on this corner, a turn on this corner, reverse the first one, and then reverse the second one. So now you'll notice that 3 pieces have changed. And that will be a trend here. If you do a commutator in a way that it just, in a way that the intersection is a single piece, you'll always get an action that like does a cycle of three different pieces. Okay, so why does it do that? Think of the piece that is in the intersection as sort of like, well, just sort of orient your mind around that spot, right? This is the spot that the 2 pieces are involved with. When I turn the first x, this piece comes into that spot. Then when I do the next y, the other thing comes into that spot. And then you undo and undo and everything goes back. Everything else that never entered this piece to begin with, or rather this location, if it didn't enter this location, that means it never had the opportunity to enter the set of moves that was changed by the other operation, right? So this, for example, we did this turn, but then undid it. So this piece didn't go anywhere because it never entered the sort of this like intersection zone where it would have been taken away by the other set of moves. Does that track with everybody?
Yeah, that helps show why there's 3.
Yes.
Because if the overlap is 1 piece, then there's a piece that got moved into the overlap on
Precisely.
the X and a piece that got moved into the overlap from the Y.
Exactly.
And there's the overlap, and that's 3.
Those are the 3 pieces, yes. The ones that will be changed are the one that enter the overlap itself, and the one that entered, the one that entered overlap from X, the overlap itself, and the one that entered the overlap from Y. So knowing that, we can sort of reverse engineer this, and if I like, here, I'm gonna do something to a different puzzle here. Let's say I have a position like this on this puzzle. The way it turns is like this. I'm trying to swap these three things. Now you can reverse engineer this entire thought process and say, what is a set of moves that has one of these three things as an overlap, and that has two of the moves are things that will enter the pieces into that overlap. Does anyone see it? Anyone who's not already a cuber?
I am a cuber on this thing are.
I haven't turned this one before.
Okay, sweet.
Well, wait, do some turns and then I'll get a feel.
This is the basic operation. We're ignoring all other operations. I'm not including like the 2x2 turns or it also does like bandaging turns like this, but ignore that. We're just thinking about simple 180-degree turns on this axis, and
So
like
if
all of
you
the other
turn-
axes like this. Yep.
Like if you turn around the edge between the white and green face,
Yes.
and then
this
turn
one.
around the edge of the white and red face, then I think that overlaps with only
That's exactly
one
right.
piece.
So before I actually do it,
That's also what I was about to say.
yeah, nice. So this is the overlap because we're turning this one and this one. So this is, the thing that you're going to enter into this position is this piece here because you're doing this. And then the thing that you're going to enter into that position from the other side is this one. So the three pieces that we're concerned with, like the three pieces that are scrambled, are precisely the ones that are going to enter the overlap and get swapped with each other. And an easy way to know in which direction you should be doing the commutator, it's always going to be like, this one is trying to go to the white side, so we're going to do that one first. That's just a kind of rule that you can memorize, is like, greedily do the starting move that puts the right thing into the overlap first. And that's just a rule that you can use to know which of the two moves you want to do first. So that's our x, y, x prime, y prime, and we're solved. And that's like the fundamental intuition behind all of this. After that, it becomes the art of actually applying this information, which is lots of pattern recognition and like experience. So I think what I'm going to try to do is just maybe I'll make a few toy examples on a 3x3 and ask you guys if you can figure out a commutator that will do the desired action to solve it. So
Before we get into that, I have
yes.
a question about the plan. So
Okay.
From what you showed, it seems like we can get, I guess, a permutation of three pieces by finding a clever commutator.
Yes.
But, I mean, I don't know enough about twisty puzzles.
Yeah.
Like, do we, like, a permutation of three, like, not every group is made out of permutations of three things. Will we ever need to, like, permute four things or two things or something?
Yes. 1 sec. Let me get a 4x4. Okay, so
Another example with the
yes. Sorry, go ahead.
ready cube.
I admittedly don't know them by name. Which is that? Is that this?
That's the first non-3x3 you showed.
This one.
Any commutator will leave the corners unchanged, so you can't solve the corners with commutators.
That's true. Yeah, you do have to know a bit about like the
corners commute.
Right. Yeah, the corners do commute. So, you have to know a bit about the geometry and like the mechanism of the puzzle before you start to apply this knowledge, because different piece types have different like group theoretical behaviors. In this case, so like if I do any commutation on two on two operations, you're always going to be doing and undoing the same thing to all of the corners. So for example, there is no corner that will like, let me contrive a position here. I hope I do this right. Yeah, so there's no commutator that will solve this, because this corner is never gonna like if I do anything and undo it later in a commutator, it's always going to go back to where it started. Does that make sense? So commutators aren't like a magic
it's
bullet.
even worse than I feared.
Yes, yeah, this is true. However, the way, like, you can apply these in very, very, very vast contexts. Like, most problems involve, maybe not most, but like a lot of problems that come up in twisty puzzles are solvable by some combination of commutators and conjugates, and I'll mention conjugates in a minute. But okay, so you asked the question of what about like two swaps, which is half of where my name comes from. Let me just do something real fast. Okay, so we have this. This is an example of exactly what you were asking about, of like two things that are swapped with each other. Like this one wants to go here and this one wants to go here, right? On the surface, it looks like this can't be solved by a commutator. However, in this case, with a bit of a change in perspective, you actually can totally solve it with a commutator. Not directly. There is no... What I mean to say is not that there is explicitly a commutator in x, y, x prime, y prime that you can do from precisely this location that will solve the two. And you can prove that to be false because a commutator has an even amount of action, so you're never going to get an odd parity operation from a commutator. However, what we can do, this might get a little bit tricky, but the idea is this. You take one of these slices and just turn it once. Now, in doing that, you have added sort of an odd permutation operation to the starting position, because we did a cycle of 4 on the edges. You're going to end up having to resolve the centers too. But now you have like 5 of these like little half edges that are swapped with each other, and that can be performed as like 2 cycles of 3. I probably said way too much, way too fast there though, so I'm going to slow down a little bit. Do you guys know what I mean when I say parity of like a group theoretical operation? Like in this case, this is a 2 swap, and what we want to think about is like how these operations can be deconstructed into 2 swaps. So, like for example, let's say I have like a set of like playing cards, or just numbers. Numbers are better. Let's just do numbers. So I have a 1, 2, and 3, and I have the ability to like swap 2 of them with each other by like doing 2, 1, 3, right? This is a single swap. We've performed a single swap of 2 items. Now, if we do, it turns out to be the case that if we do any amount of swaps of 2 items, you won't be able to recover a position that you could have gotten from the opposite parity number of swaps. So that is to say, like another way of saying that is there's no way that I can ever do an odd number of swaps and come back to 1, 2, 3. So the amount of swaps of 2 items that you do is going to be, how do I say? It's like, it's kind of invariant. Like the amount of positions that you can get to, I'm losing the words here. Like in the case of this puzzle,
you have an even or an odd amount of 2 swaps. Exactly.
Yeah. For any given position that you're at, that has a distinct parity to it, and so that informs you of how many moves you're going to have to make, like how many quarter turns you're going to have to make to go back to the starting position. For example, like if I do something, I've now swapped 2 edges and 2 corners. Now, since I've swapped, we'll just not think about edges for the time being, but since I've swapped 2 corners here, I know that the amount of quarter turns that I'm going to have to do to solve this cube is an odd number of quarter turns. And the reason is, each time I do a quarter turn, it's doing an odd parity element. And I'm now realizing I need to explain exactly what makes a cycle of 4 things an odd parity element. So if we have like 1, 2, 3, 4, and we cycle this to like 4, 1, 2, 3, the amount of two swaps that it takes to go back to the starting position is 3, or an odd number if you want to do it like really inefficiently. But like we can swap the 1 with the 4 here. So this is the first operation. So now we have 1, 4. Now we swap the 4 with the 2. So 2, 4. And then swap the 4 with the 3. So that was 3 operations that we did to go back to where we started. And in general, a cycle of n elements has the opposite parity as the like evenness or oddness of n itself. So like for two things that are cycled with each other, like a 2 and a 1 that are cycled with each other, 2 elements has an odd parity in terms of when you do the cycle. Like it's an odd group element. If you have 1, 2, 3, that's now even, which we indirectly saw earlier, because when we did x, y, x prime, y prime, we necessarily did an even amount of actions, and we yielded a cycle of 3 things. Does that make sense?
Wait, I made a video on my cubing channel about why 4x4 parity happens. So
Okay, you should link it in the chat. Self promo is totally allowed.
Yeah, that's good. That's good. Self promo time. Okay, wait. Let me get the link. Yeah, this video is from like almost a decade ago, but the math has not changed since then.
Yeah. So with this 4x4, like we can do things like this, which has a cycle of 4 objects, and because it has a cycle of 4 objects on these edge wings, you end up with the ability to like swap the parity of the edges as a system by doing a single one of those. So in order to get out of the parity where we can't solve this with commutators, we can just make any single like slice turn like this. And now we're in a position where commutators are our friends again. I could explain how you could actually do this in practice with a commutator, but I think it's a little bit crazy. So I will pass on that for now. Do you guys get the concept though? Like the general idea here makes sense. Let's do another example, just to keep it grounded. How about this position? So there's like 3 pieces that are swapped with each other. This one wants to go here. This one wants to go here. This one wants to go here. How would you fix that?
Twisting that corner with
What?
only the inner. The
What is that
facing
corner?
You.
This one.
Yeah, that corner with only the inner ring.
Yes. Okay. So like this, you're saying.
Yep, and then the corner on the top left there with both the rings.
This one.
Oh, I see. I wasn't sure
And
how this
twisting
twisted, but yes.
That first one back and twisting that other one back.
I have bad news. That is not it. You're very close though.
Here, other way?
Yeah. So remember the rule of thumb here is figure out what your intersection is. Like figure out what your overlap is, which is in our case this piece, right? Because this one goes down here, this one goes down here, right? And then the first move that you do is just the thing that goes into the thing that wants to be in the overlap. So we're gonna put this one into the overlap to start, then do the second move, and you'll see it start to already come together. So now this one's flush with all the pieces that it wants to be next to. Then undo and then undo. And just like that, it's solved. So by composing commutators, you can basically solve this entire puzzle. This one doesn't have any substantially harder challenges than the things that we've mentioned so far. If I were to scramble this up entirely, you could just go by sets of 3 over the edges and solve the edges that way. You'd have to also work out these two, but like it's also not that challenging using commutators. Okay.
Do the corners on that one also not?
Yeah, exactly. So I'll just go ahead and explain the entire way that you solve this. what a nice thing to notice is that it's actually basically the same as this puzzle in terms of the corners and these sort of like wedges like this. I don't know what to call them. But like, you know, this edge behaves in the same way that this chunk of 2 pieces acts. So like this is basically just this plus these little tiny pieces on the inside. Okay, so how you solve this is basically you first solve this part, and the way that you solve this part, let's just scramble it up. You guys can probably figure it out at this point.
Well, I imagine you can just like solve the corners first.
Bingo.
And ignore the edges, and then and then use commentators for the edges.
Yeah, so I'm just gonna go ahead and solve the corners. There's no challenge here because, as we said, they're not commutative, so you just greedily insert corners one by one. I didn't scramble it very well, so I've ended up with most of the edges already done. But like, okay, pick. Can anybody see any corners that they want to solve? Call some out.
Edges?
Yeah, edges. Sorry, did I say corners?
White, blue.
White, blue. Okay, white, blue. Now, what else? We're going to do a cycle of 3 things. So tell me what the cycle of 3 is going to look like.
R prime, L prime.
Well, hold on. Tell me what else you're going to solve too, before we.
White, orange.
Yes. Okay. White, blue, white, orange. What else?
Nothing else that can be solved, but it's going to touch FL.
Yeah. So okay, what he's saying is we're gonna take this one, and this one, and this is a nice combo because this one wants to go here, this one wants to go here, this one doesn't want to go back here. It's not a precise 3 cycle, but what we're going to do is solve 2 in the chain here. So we're gonna solve this one by putting it into the spot that it wants to go. We're gonna solve this one by putting it into the spot that it wants to go, and then this one's gonna in consequence end up here, but we don't really care because we're solving 2 things. We're getting closer. So could someone else tell me how to actually do the commutator?
You twist the top right corner there.
Okay, like that.
Yep, and then the left one.
Oh yeah, yep.
And the right one back, and the left one back.
Yeah, good.
The
So
left one, why did we turn it
here,
in that direction instead of the other direction?
So these are the 3 pieces that we're trying to move, right? This one is the overlap. This one is the one that wants to go into the overlap.
Yes.
And this one is the other one that wants to go into the overlap later. So we're going to turn this one down into the overlap, and this one comes up into the overlap. Right? It's these 3
yeah,
that
we need to move the 3rd piece so it goes into the overlap.
Yeah.
Then we have a commutator. Okay.
Exactly. So this one's coming down into the overlap. This one comes up into the overlap. And then undo. Okay. Anyone else see any nice things to do here? I have the chat open. Are red, white, blue, red, white? Oh, sorry, I missed your answer. I saw letters and I was mentally flustered and didn't know what to think about them. Anybody want to give me a crazy idea for what we should do next? Letters are confusing. Sorry.
Well, I was gonna say, like, in the first commutator, it was kind of lucky that like a 4-move commutator could solve 2 pieces, but like,
Yep.
Maybe, you know, if it's not as lucky, we have to settle for just solving 1 or something, and then.
Okay, I'm glad you said that.
Like,
let's not settle. Let's force ourselves to be able to solve 2 at the same time.
Well, I guess because the red-blue edge is like 1 turn away.
Yeah, bingo. That's good. That's a good observation.
But then like the white-green one that's like in that spot is like, I feel like it has to go far distance. And
it does have to go far distance, doesn't it? That kind of sucks. But okay, so here's the next group theory lesson. So we've talked about commutators. Now we're going to talk about conjugates. So a conjugate is just something like x, y, x inverted. Now, this is helpful for different reasons. I think a good way to think of it is like if you've learned like linear algebra, basically what you're doing is just like a change of basis here, right? If you can imagine that this is like a matrix that is like changing something, like y is doing something, and we're just doing some kind of setup on either side. Like we're doing a setup and then undoing the setup. In the context of a twisty puzzle, I'm just going to tell you offhand that I know a commutator that can do this. So I've taken this one, like this corner goes here, this one goes here, this one goes here, right? We're just gonna take for granted that we know this, we know how to do that. Now, what happens if, hold on as I set up a contrived situation. If we actually, I might have made this a little bit too hard. Hold on, please hold. Okay, what about this? So we had a commutator which cycled this piece with this piece with this piece, sort of while maintaining their orientation on the top face. Now what we have is this piece, and this piece. So like one thing you could do is like solve one of these pieces, and then like, but then you would just end up with like another set of three pieces that you have to solve. So it's kind of unhelpful if you don't have any more clever way of going about the problem. And this is where conjugates come in. So does anyone want to guess before I spoil what you should do here? I think you're saying this? Okay, yeah, that is exactly right. So the third piece, if we have the third piece here, now when we do our commutator, like swap this one with this one, this one, this one, and like do our cycle on these three pieces, we've now like fixed the three that needed to be fixed, and then we're just gonna undo that setup move. So I'll just go ahead and do that. And now, so that was our, to be clear, our x was moving this face like this. The y was the first commutator that we came up with. And the x inverted is just putting this back when we're done. Now let's try and use that for this one. We're here, and we're like, we know that we could solve one of these, but we want to solve two at a time because we're cool like that. So how are we going to do that? We can say like, let's just say that we're going to solve these two. And we don't care what the consequences of it are. We're just like, we don't care how hard it is to do that. We're just going to do it anyway. So where does the green and white go? It goes here, right? So we have this piece, and this piece. And those are the three that we want to change. Now, what can we do as a setup move such that a simple commutator would be cycling all three of these things? This is now basically...
Here.
Yep. Sorry, go ahead.
Your near right corner rotated clockwise to get that yellow edge piece closer to the other pieces.
Yes, great.
And then do a cycle.
Exactly. Yeah. So okay, that's the setup move. That is a working setup move. What's the commutator now?
Well, okay. Is it like the left corner down?
Yeah.
Right
So
down?
well, before you, yes, you're right. But before we jump in, where's the overlap and what are the two pieces that we're moving? Just so we have a sense of what, like, let's show our work.
Oh, well, the overlap is the white green piece that's like right in front of you.
Yes.
And that's like the intersection, like with the left corner and the right corner.
Yes. So And the two pieces that we're modifying are, as we mentioned before, like this one and this one. So these two are going to want to come down into the overlap. So we're doing like moves that are like this and like this. And the order that we want to do them is the one that solves the thing that wants to go to the overlap. So this one wants to go to the overlap. So we're going to put it down first. Then we're going to put the other side down. Then we're going to undo the first move and then undo the second move. And now we have this move left to be done. And that is a
commutator. Or sorry, the conjugate.
Yes, exactly. So now we've undone our X. And we're left with only 3 pieces left to go. Because we were ornery and we didn't care how difficult it was to do that complicated action. My roommate needs me to move my car, so I will do a setup move so his car can do a... wait, what's the... Yeah, exactly, yeah. So that's the other thing, is like a lot of these things, you'll start to see them in daily life contexts once you have a handle of them. Like, yeah, so if you have 2 cars in a driveway, and like, here's your house. This car wants to go to the grocery store. I don't know if it's really a commutator when you go to the grocery store, but this car is going to back up like that. So that's your X, right? This is your X action. This car is going to go out, do something, come back. So this is just a Y. And it's going to end up back where it started. And then you do the X prime where you move the car back. Right? That's a simple conjugate in daily life. Another great example with parking is parallel parking. If you kind of squint hard enough, parallel parking is basically a commutator. So like here's the wall that you're trying to parallel park against, right? And here's the position that you want to be in, right? Actually, no, we'll say that's a car that's already there. This is a car that's already there, and you're trying to get into this spot, and you're here. No, you're here. You're here right now, in the middle of the street. So how are you going to get into this spot? You're going to go forward, so that you're in this spot. Hold on, I need an eraser for this marker because it's. One second. Okay, so you're in this spot, and you want to go rightward, but you can only move forward and backward and change your angle. That's the premise that we have here. So you're going to move forward, which is your X in your commutator, like this. So now you're here. Now you're going to change your angle, which is your Y, and specifically you're going to rotate counterclockwise by like a few degrees, like this, right? Then you're going to move backwards. So that's your X inverted, and now you're like here, but like tilted at a weird angle. And then you're going to turn your angle back, like that. So the idea behind these commutators and conjugates is there are ways of sort of changing your reference frame such that you can do an action that wouldn't have otherwise made sense. Like in this
one, would you not just be able to turn 90 degrees at the start back in?
You could do that. You could do that. You could also do that. That would be a great example of a conjugate. Yeah. Just twist. Yeah, twist 90 degrees in spot without moving. But like that would be a great example of a conjugate, right? So we start here, we turn 90 degrees, so that's our X. We turn 90 degrees so that we're facing this way. Now we move into the spot, so that's our Y now that we just did, and then we're going to turn 90 degrees back. So that's X prime, or X inverted.
This is called perpendicular park.
Yeah. Okay, so that's a great example of how these show up in context outside of twisty puzzles. Another puzzle that I've already mentioned in the chat here, but I'm not sure if everyone knows the answer to. I'm going to spoil it. You have two. The original puzzle is like you have a painting that's hanging from the wall. Sorry, the camera's all blurry. You have a painting that's hanging from a wall, and you want the painting to be hung around like 2 pins. So I'm going to use this rope to be like the painting. You can imagine there's a painting holding these 2 ends together. but like, you know, it's really just a knot. Like this is just a tied loop around the two objects. Now, how would you, the question is, how do you like loop this thing around such that the painting hangs from these two objects? However, the painting is non-redundantly hung, such that if you remove either of the two pins, it will fall down. So this isn't a solution here, because if I remove this pin, the painting will still remain hung on this pin. So that doesn't work. How do you solve it? The answer is basically just do a commutator. So we're going to imagine the rope starting here, and then we're going to do an action of X, which is going clockwise around this pin, and coming back to where we started. So that was our X. Now our Y is going to go clockwise around the second pin. X inverted will go counterclockwise around the first pin. And then Y inverted is going to be counterclockwise around the second pin. And you get this little knot here, such that whenever I remove either pin, the whole thing just comes undone. And the reason that works is because all we're doing when we do that is like cutting out the X and X prime or the Y and Y prime in our commutator. So like by removing a pin, we just delete all of the Y related things such that the X and X prime collide with each other and cancel out to 0 to the identity of your group. And this can be used to generalize this solution to as many pins in the wall that you possibly want. So like for 3, you can do it by going like basically do a nested commutator. We're gonna go one around the left, one around the right. Sorry, one around the middle rather. We're just gonna do the same thing that we did for the last solution. But then that's the first element in our super commutator. Now we're going to go one cycle around this guy. Now we're going to undo our first commutator, which I don't know if I have enough rope to do here. Try and grab some more. If we undo our first commutator, we're going to go X, Y, X prime, Y prime. We're going to go Y, X, Y prime, X prime. And now, still not enough rope. Just have to get it around the Z in the opposite direction as before. Which was, I went clockwise? I think I went clockwise. So we're going to go counterclockwise this time. Now, barely enough rope to do that, but anyone want to select which pin I should pull?
Definitely the one on the right.
Okay, we're going to pull this one out, and hopefully, if I did that right, everything else should just fall off. Like magic. I can't believe that worked on the first try. Does that make sense, though? The idea is, the principle is the same. We're using the fact that, like, these two group theoretical ideas are tangled with each other. Like X, oh, that's very, very much not visible. Hold on. Like X and Y, like X and X prime want to collide with each other and form the identity, but Y is like getting in the way. And that is how you can use a commutator to make something that wants to be the identity not be the identity, if that makes sense. In very informal language. But like, you know, you can keep composing these. You can keep making like, you know, you can do your Z, Y. We're now inverting this whole thing. Y, X, Y prime, X prime, Z prime, that's what we just did on the string. Make sense? I could not make out what you said. What was that? There are solutions to this problem that do not contain commutators. Yes, yeah, that is true. Another way of thinking of this is like you're kind of walking on a coordinate grid. So like, imagine like you have just like an infinite coordinate plane on like two dimensions. I'm just gonna draw a couple points here. you can think of X as like the action of going upwards, and Y is the action of going rightwards. And that way, like your commutator can be like viewed or visualized kind of like this. You end up back where you started, but at each like section of the operator, you're doing some kind of like, how do I say? This is a commutator. That's my point here, is you're doing a commutator here. However, you can do a non-commutator action by making another cycle that goes back to the origin on this space that isn't directly a commutator in the first place. So like a good example of that would be like x, x, y, y, x prime, y prime, x prime, y prime. If I got that right. I believe that is not a commutator.
Representing, or what is the goal here? I've lost track.
I'm representing our action with the rope on that set of pins, abstractly using this different kind of diagram, which is where like the x direction, the direction of doing x, is going up vertically, and the action of doing y, that is looping the thing around the right pin clockwise, is going rightwards. On this diagram. So what I'm doing here is I'm constructing a different solution that is not a commutator, because Axiomatic System in the chat said like you can make non-commutator operations. So that is exactly what I'm doing here. And I'm going to actually now string up this example of the thing that I just drew on the paper. So it's saying we do x, x, y, y, x prime, y prime, x prime, y prime. So x, x, y, y, x prime, y prime, x prime, y prime. So this is not strictly a commutator in the sense that it can't be written as like some x, some y, some x prime, some y prime, right? Actually, can it not? I'm now doubting whether that's the case. In this form, it is not written in that form the way that I've presented the sequence, but I'm wondering if there's some way that you can make it like make two bordering elements like cancel each other out such that it came from a commutator where the like intermediate spots like canceled with each other. I'm not sure, but it at least doesn't look like a commutator. So now if I pull one of these out, it still comes undone. It's a free group. I don't know what that means. What is a free group? Please help.
Free group.
Free group is like,
Or Jacob, if you want to talk.
No non-trivial relations between the elements.
like a language with composition by putting things next to each other.
A language, so just like
there's no secret identities, and so you can kind of see on the diagram you drew to swap that it's not like there's no commutator in there.
there's no
because
well, but
it
I'm
would have to look like a commutator.
I guess you're right. Yeah, I think you're right. But like what I was
Or
wondering,
the rope problem.
not about secret identities, but just like implicit identities where you do this. Like where you go up and around like
No,
like
so certainly x inverse is the identity in
Right.
all groups.
right, exactly.
But like some other things you write down are only the identity in some groups. In a free group on x and y, nothing you write down is the identity unless like it obviously
Unless-
reduces the identity
yeah.
because the inverses.
Yeah, but what I'm suggesting is maybe I mean maybe I'm totally wrong here, but what I'm wondering is maybe this can be written as a commutator, which takes advantage of the fact that like compositions undo consecutive things. Does that make sense?
In that I don't want to write out the proof that it can't happen right now, but that can actually happen.
I feel like maybe it's generated by commutators because if A and B don't commute, and that's within the subgroup that's generated by commutators. And so if it's outside of the commutators, then A and B should commute, which means this would be the same as not going anywhere.
Sorry, can you say that one more time? I didn't get that.
If A and B, if you have A and B not commuting,
Mhm.
that's within a subgroup generated by commutators.
Yeah.
And so anything outside of that subgroup, they should commute.
Yeah.
So here, this would be the identity.
Yes.
It might be a
Wait,
commutator, is what I'm
so,
saying. I
wait,
feel
why
like
do we
it might be.
care about... Wait, so you're saying that, like, this loop can be written as a product of commutators, even though it
Maybe.
doesn't...
I don't know, but like that to me that feels like kind of cheating the question a little bit because like we're concerned fundamentally like at the end of the day this commutator is just the identity. So like whether or not like we were really concerned with the way that we were writing it in the first place. So I think this is kind of a meaningless addition to the question insofar as this can't be written directly as like it using like the x like this notation. I think it kind of satisfies the implicit question that we were asking whether or not there is a way of constructing it in by invoking like x times x inverse equals 0. Does that make sense?
Yeah, I think it would take us a little too far afield because you're not giving a talk on...
Well, that's what Math Club is for. This is kind of, admittedly, this is kind of the sort of thing that I hoped this would turn into, is like people start to talk about completely unrelated math problems, because that's fun. But anyway, aside from that, how do we solve this? This is what we were doing, right?
About to mention, because I feel like I know exactly how. You
Okay.
twist that corner so that it lines up with the other three.
This one, like that, or
Yep.
like that. Like, do we want it to go this way or do we want it to go this way? This way, you're saying?
Yeah.
Okay. Now what?
And then you twist that left corner down.
Tell me what the things that need to. Yeah.
Yeah. The 3 edge pieces facing you.
Yes. Okay. These 3 need to change, and the.
Yeah. So that left one twists down.
Yeah.
And the right one twists. Looks like down or up. Does it matter?
It does matter.
Yeah.
So the buffer is the overlap is here. So we're gonna.
Yep.
So we want to put both things into the overlap, and the other thing that we're trying to put into the overlap is here. So we're gonna move that down. Then
And
we're
then
gonna
undo.
yeah undo, and then undo your conjugate like setup.
And that looks solved.
That is solved. Congratulations, you solved a twisty puzzle. Thank you. Yeah, so that's basically like what it comes down to. After that, a lot of it is just like, can you be clever about how you're making commutators, like understanding the puzzle, knowing what its geometry like sort of supports can be very helpful. Just as a motivating example of how you can sort of continue to build on this and use clever tricks to do things with commutators. Let's say you have a situation like this on a standard 3x3 Rubik's Cube. Camera, please.
When you move your hand, your camera has to compensate, like blurs for
There
the
you go.
motion, and then it's harder to see. Like if you somehow didn't move, then we'd be able to see perfectly. Like, how would you see it?
Yeah. Okay, so imagine you have a position like this. So what's going on here is it looks like there's this slice that wants to be here and this slice wants to be here. Now, first things first, this is not in the format of 3 cycles that we've been talking about so far. There's like 2 things that want to swap with each other. So step 1 is, can you come up with a way to translate this into a world where we're doing a cycle of 3 things? There's a very clever way to do this from this position.
Is the side to the right of the green orange? Yes, okay.
Any guesses? I'll give you a hint. It is you can do a single move that transforms this into a place where you're trying to swap 2 things to a place where you're trying to cycle 3 things. No takers?
With no experience with twisty puzzles, I cannot figure it out that fast. No.
Okay. Cubers can join the fray here. No?
You gave the answer. You can do a single move.
Yeah. What's
and
the?
It doesn't matter. But I would pick you.
Well, yeah. Okay, yes, yeah. You can theoretically do any move, and is that true? It
might take more than one commutator, so I choose you.
Is that necessarily the case? Does it necessarily take more than one commutator? Yeah. I don't actually know.
Oh, well.
Like arbitrarily complicated commutators.
Yeah, like if you moved L, then you would have a 5 cycle, which for at least
sorry, to be clear, what I'm saying is, yeah, this is a 5 cycle on both the edges and the corners, but like I'm not talking about the simple commutators I presented today where you have an overlap of size 1. Rather, is there no arbitrary action?
I haven't delved into commutators that work 3 pieces.
I missed you. What'd you say? You haven't delved into
I haven't really looked at.
I see. Yeah.
That
I suspect but don't know. I'm sure this is a known result in group theory, but I suspect but am not sure whether all even parity elements of the Rubik's Cube has a single commutator that solves them. Or that
in a general group, the set generated or the subgroup generated by commutators is not necessarily just commutators. Like you can get things by composing commutators that is not a commutator.
Right.
The set of all commutators is not a subgroup.
Right.
That might not be true for the cube.
I think it is, but I'm not. But I don't have a proof. That's just my intuition and gut feeling speaking. But okay. Anyway, you said you being this. So why is this a good move? Can anyone articulate to me why this ends up with this position that you're trying to swap or cycle 3 things? I think you said you have 3 sets of pieces that are all out of place. So that being this one, this one, this one. So to be clear, we're talking about pairs now. Like we're not talking about individual pieces, but we're trying to do a 3 cycle on pairs. So how can we do a commutator on pairs? Yes, pairs with an E. I'll kind of unless anybody has an idea, I'll spoil the answer on this one.
I mean, we want to move 2 things. We want to move a pair into the overlap, right? Or like into the center of the 3 pairs somehow. I guess you can't just rotate the top. That's not going to work, I guess. So I don't know.
I'm now realizing this may be a more difficult example than I immediately thought, because my...
Yeah, I would usually do that with a conjugate.
Yeah. Shoot. Yeah, so like, okay, I'm gonna, this will be a little bit more complicated, but I'm gonna do it anyway. What I'm gonna do is I'm going to do a commutator that solves pair 1, 2, it's gonna cycle this one, and some other unknown pair. Then we're going to cycle that unknown pair and the remaining unsolved pair. We're going to do 2 commutators to solve this. So step 1 is going to be our first commutator, and our goal is to just solve this one. And we'll ignore, we'll not necessarily solve these 2 here, but we're going to solve this one. So I'm going to call this pair here the overlap. We're going to put that pair into it. Now what I'm going to do is scramble the rest of the cube somehow. And the way that I'm going to do that is by doing this. So I took that pair out. Now I'm going to undo our x. This is probably way too hard to understand. Then, are you guys following me? Do you see where I'm going with this?
So the thing is, by the time you said took that pair out, I wasn't prepared to memorize the colors of the pair you were looking at, and so lost track of what was going on.
Okay, so hold on. Let me construct an easier example here. Okay, let's do this. No, let's not do that. I have become lost. Okay, I'm back to solved. Let's just do here. I'm gonna construct the problem with a commutator such that I know that it's solvable with a commutator. Okay, we're here. Instead, it's this pair, and this pair. So, what is your intersection, or rather your overlap going to be? And how are you going to like modify these 3 pairs?
My guess would be that the blue on the top is going to go into the interference, which is going to be that face turned clockwise.
This is the interference, you're saying?
Yeah.
Okay. Why do you want that to be the interference? Here's one thing to remember. The interference should be something that is easily reached by... It should either be one of the elements or easily reached by the other 2 elements. If you select this one to be the overlap, then the annoying thing is there's no easy way to map these 2 pieces onto that overlap. Like if I turn it down, like one of them goes into place, like the edge goes into place, but this one doesn't go into place. You might have to do like a sequence of multiple moves to like get it in there. There is an overlap here that does not involve, well, that
top right.
How do we get this one into the top right? How do we get this slice into the top right?
Oh, I see. This is the same problem.
Yeah, same problem backwards.
So the blue on top is already the interference?
That's the interference. So if this one goes like this pair ends up in the interference, like that. If this one turns like this, it ends up in the interference like that. So this is a nice interference. Okay, now, how do we do this? Slightly... I'm realizing my examples are way harder than I think they are at the get-go. This still has a bit of a challenge to it. I think it's easier than the last one.
So if the top left is the interference, then the thing that goes there first would be what's on the top right. So rotate
okay,
the top clockwise, and then you want to do
you're gonna want to put the other thing into the
solid
intersection. Yeah. Now you're gonna undo the first one and undo the second one, and oh no, what happened? We solved the edges,
I broke it.
as a matter of fact. However, in this case, you have to be a little bit more clever. So the reason that doesn't work Can anyone figure out the reason that doesn't work? It has to do with an asterisk that I have said so far in this talk. What do you want the intersection to be? I think you're saying you want it to be these two. Yes, that's correct. You want the intersection to be like a single thing that you're acting on. In this case, it's really a single pair. What is the intersection in reality that we just did? Like the two.
The whole three.
Yeah, we messed with this whole slice, and because of that, this thing and the stuff that got inserted into this spot, also got scrambled or also had some kind of interaction with the commutator. We don't want that. So the new question is using this as the like intersection. How can you get this in and get this in such that not both of them involve touching this? I think there's actually two equally valid ways of doing this. One involves, making this pair not touch this one, and one involves making this pair not touch this one. I'll give you a hint. It's a 3-move operation. In both cases.
Just to be clear, is this 3-move operation we're looking for something that we could find with like conjugation, or because that's the only like 3 thing we've talked about in this talk?
BFS. No, but yes, you can find that. You can find it with conjugation.
Wait, are we doing a block commutator?
Yes. I didn't even know that was what it was called, but yes, I think so.
Is this one R wide prime D prime R?
Yes.
U, R wide prime D R U prime.
Spoilers.
Oh no.
Okay.
Well,
no, that's okay. That's okay. No one knows the notation. We're good. We're safe.
Okay.
The question is, how do we?
I have literally no idea how that notation even works. Kinda.
So we just tried and failed to do this. But the problem there is that both of the X and Y interact with this entire row of 3 pieces instead of just this pair. And because of that, you're having undesired consequences that involve things moving into this corner. So the question is, how do we use a conjugate to move one of these 2 pairs into this slice without also having problems with this thing? Any crazy conjugate ideas? What is the goal of our conjugate going to be here? And maybe somebody just pick one arbitrarily. I'm gonna spoil it that either of these 2 pairs can go into this spot without a hitch. Which do you want to pick? Let's just pick one.
Let's see the top ones go in.
Okay, these are going to go into here without messing with this corner, which is not the one that Carrie said. So, how are we going to get these 2 into this spot without interfering with this thing? A question that you can ask yourself is, what can we mess up? What is free to mess up that doesn't involve, like, insofar as we're selecting these 2 as the ones that want to go in, our Y we now know to be this, right? So we need
back left face.
Yeah. This whole section is like free real estate here for us to do whatever the heck we want.
Wait, that's not the face. Wait, that involves the cube we want. I meant the other face, the back, your left.
This thing.
Because that doesn't have any of the pairs, right? That's the
but
face that doesn't have a pair.
But our Y is this. What we're concerned with is that Y doesn't intersect with this stuff. And if we do that, if we mess with this face all over, we're going to have our Y touch this thing and our X also touch this slice of 3. So that would be bad news.
Okay, yeah, that's bad. But the thing you were showing has part of a pair in it. So that seems
That's
very
true.
bad.
Well, we need to move the pair. Like the goal was to move the pair. The conjugate has to touch the pair. Because that was like the stated goal of the conjugate to begin with. How do we get...
I thought the conjugate was to set up something so that way a commutator won't have a problem. I thought that was
Yeah.
So I misunderstood.
Yes. Okay. I see. I see the confusion. So, like, if our commutator is A B A prime B prime, and I'm writing right to left to right here to be clear, if it hasn't become obvious, because that's sort of the typical Rubik's notation. If we're doing A B A prime B prime, I think what you were suggesting is that we wrap this whole thing in a conjugate like x prime, like that. That is not what I'm suggesting. What I'm suggesting is that we figured out our b or our y to be this front term. However, I'm suggesting that our a should be a conjugate, and therefore our a prime should also be a conjugate.
Due to my lack of experience with this stuff,
Yep.
I had in mind neither of those in a way that like definitely doesn't work, and now I understand why it doesn't.
Okay. A is going to be a conjugate. We're trying to get this thing here using a conjugate such that it doesn't interfere with anything on this face. That's our goal. Now, I suggested you could use this face. So how could you do that? How could you, how could you like take advantage of the existence of this face that doesn't have any intersection with this to get this thing here? I'll give you a spoiler of what the starter move should be. This will be the starter move. Or alternatively, it might make more sense to view it as this. Actually, that's probably a much easier way to see it.
I said at the beginning. That was the thing I said at the beginning, that we should do the back face. When I see the
yes.
solution, maybe I'll get it.
Yeah. I think you'll see what's going on in a moment. This is the piece that we're having issues with, right? That's the piece that we accidentally screw up, right?
Yeah.
So let's just move it out of the way. That's going to be our x. Like if a is equal to like if a equals x y x prime, right? Then if our x is just moving this thing out of the way, then we can do y, which is the move that we wanted to do to begin with, then do our x prime, and we're safe, right? Because we did and undid the thing that acted on this side. That's how we use the conjugate. We move this piece out and then put it right back.
Okay.
Does that make sense? So that's our A. We're now going to do B, which is this one. Now A prime is once again move this guy down, then put this like that, and move it back up, and then B prime, which is to turn the front face. To be clear, this is like we're already at like 2 layers of nesting and doing like a commutator that acts on 2 things at the same time. Like this is already in like not beginner territory, to be clear. But did that make sense? Do you get how we did that?
Yeah, I think I had the right start in my head, but didn't fully understand what was going on. But now that you explained it in terms of the notation, I think I understand it.
Cool.
So, thank you.
Yeah. Sweet. Now what? What should we do? We could talk about crazier commutators on even bigger puzzles. Or we could not.
Well, so...
Yes.
Oh, for axiomatic systems. Something.
Yes. I think he said, just to make sure I'm understanding.
In the beginning, when we had that problem situation where the simplest value didn't work, that was just a free segment that we could have solved by our earlier commutator, right?
I think you're talking about, are you talking about this one where we were here?
Yeah, when we did the simple solution with the three piece intersection, and then we ended up with something we said was wrong.
are you? Is this what you're referring to? Where we had these three?
The three pair problem we just did, and then you started off with the like basic commutator trees, and it didn't quite work.
Right. Yeah. Okay. What's the question about it? Here, let me reconstruct it. Yeah, we were here.
And then at the very beginning of solving this, we just did the very simple commutator where we just put the pairs in place without worrying about moving pieces out of the way.
Which was this.
Yeah. This is just a simpler problem that we could solve with our earlier method, right?
That's true. Yeah, that's totally true. You can, like, having done that, here, let me go back real fast. You can break this down into an edge problem and a corner problem. So like we have three edges that are flipped with each other. Like this one wants to go here, this one wants to go here, this one wants to go here. So like we can totally do the edges as a sub problem of this, and then do the corners and vice versa in the opposite order. That's totally fine. You can totally do that. And let's go ahead and just give it a try. I just wanted to show the single commutator that does everything. How would you do this though? Huh? I missed that. You didn't really like it? You didn't really like the complicated commutator? Is that what you said? Okay. Well, the commutator doesn't like you either, but we can do this with a commutator, and that will be simple. Any ideas? How are we going to, like, what's our intersection going to be? Oh, you said you did like it. Okay. Good. Yeah, it's a good commutator. How are we going to solve this?
Wait, for this one, I guess there's the orange, yellow, blue corner that will become solved if you turn the blue face clockwise.
Yes. That's true.
So,
what about this one?
and then for the other moves, I think you could. Well, it would be like I want to use like cubing notation, but it's like a 3-move insert, so it would be like.
Well, before you say the 3-move insert, what is the action that gets the other thing into the buffer, or into the intersection rather?
Well, I'm trying to get the blue, white, orange corner that's on the left. Like I want to also try to get the intersection would be that lower. Or no, I was thinking the blue, white, yellow, blue, white, orange corner.
You're gonna have this one be the intersection?
No, not the intersection, but that's the one I'm trying to insert into the intersection.
Yes. Yeah. Okay, so we know how to insert this one. In theory, we could insert this one like this. Does anyone want to chime in and say why we can't do that in this context? If our x is this, why can't our y be this, right? We're selecting this to be the intersection, and we know how to insert this one into the intersection. We also know that doing this would insert this one into the intersection. What's wrong with that?
Because the overlap is too many pieces.
Spoiler, I was hoping someone new would get it. That's okay.
Oh.
No, you're good.
Yeah,
Okay,
it's like a lesson for like me and Naifakosi.
Yeah.
Like the only ones who don't cube or something.
I think there's a bit more. I think Carrie KH and the Gray Cuber are the only people who are like knowledgeable cubers here? Question mark? I don't know. Maybe I'm wrong. But I don't know.
I guess I won't spoil if
That's okay. You're allowed to spoil when on the hard problems.
Oh, okay, cool.
Okay, so the reason, so as Carrie said, if we try and insert this one like that, these two end up getting, like, they're in the intersection of x and y as well. So x is this, y is this. These two pieces are in both of those, so they're in the intersection, and that's bad. So how do we avoid that? I'm going to say our x is going to be this. You could also make x different and let y be this, but we'll say x is this, and we want to insert y while somehow avoiding messing with these two. How would you do that?
After you do that x, can we rotate the front face? Because the pieces you moved into place are
Which one's the front face?
Wait,
This one, orange?
yeah, the one facing you.
Like that.
Yeah.
Ooh, that's a good idea, but there is also intersection issues there. Can you figure out where?
I need to think like the moves ahead. Hold on. So we do that.
Well, just think of this and this. Those two actions alone, like doing this. What is the intersection of those two moves?
Oh, and then it's like the 3 and the front right,
Yeah.
which is
Right.
too many because even though you brought them from elsewhere, you don't.
That's
have that
true.
problem.
Yeah, this edge is going to get scrambled for sure if we do that. Furthermore, there's another problem with that, which is the way that we insert this. Like, we want this sticker on the orange to be going into like the equivalent orange sticker on the intersection, right? We want this to be inserted like this. Wait, is that? Am I lying? No, that's a lie. Yeah, never mind. Sorry. Yes, you're right. Okay, yeah, never mind. Sorry. Continue. You're on the right track. You want to do something like this. You can create a conjugate that will do what you want without having adverse effects. In the same style as the one that we just did, like with our A being like a conjugate. Here's X. We want to implicitly turn this front face without messing with these two, right? So how can we avoid messing with these two?
The face in your left hand should be moved, or move the other 2 layers, because that's the problem. The
like
problem
this?
lives on those layers.
Is this what you're saying?
Something like that.
Exactly. Yeah.
I don't know what direction.
Yeah. No. So yeah, if we take these two, you're trying to do this turn. If we move these two backwards like that, then we can freely do this turn while only messing with stuff that was down here that we didn't have in our intersection to begin with. So we're now putting this one in, undo our action there. So that was our conjugate. We wanted to do this, but we couldn't just do that because it had this intersection problem with our X. So we moved those two pieces out of the way, did the thing we wanted to do, and unmoved them.
Yeah.
So now, tell me what to do. You should know the continuation from here.
That requires me to have stored in my mental memory, like
what was
are
X?
we in the sequence? Like if I had paper.
We just did XY.
Whatever one.
So we did XY. So our X was like we did an X and then we did a Y, which was underneath it was an A, B, A prime. So now we have to do X prime. Do you remember what X prime was? How did we get this thing into this position? You can also kind of just look at it.
So yeah, rotate it so the white face is at the bottom. Yeah, like that.
Yeah, exactly. And now undo our conjugate.
And so it's at this point where like I would look at whatever moves I wrote on the paper.
Yeah, you can do that. Yeah, that's fair. Okay, I think I've gotten the point across though. It seems like everybody's following how you make these in practice. Yes? Anyone feel lost? I'm gonna show here. I'm gonna do a little show and tell here. This is a little program that I made a while ago. One sec as I get out of screen record mode. So I get into screen record mode. Please hold. Can you see this? Now, I partially just want to bring this up because I'm curious if anyone knows of something that exists that is like what I'm about to show you, but it is a completely generic and puzzle agnostic solver of group like twisty puzzles like this, and really it just acts on arbitrary permutation groups. So this here is a Rubik's cube, but like it's just the stickers are written out, and the program under the hood knows like what a that a twist involves, like, you know, rotating 9 of these stickers and another 12 of them, like for the 9 that are on the face of the cube and 12 that are around that face. So I made this thing that literally just invokes the application of commutators with a search depth of, I think, just 1. I say I think because I did this like a year and a half ago. But it'll solve your cube like that after a relatively short amount of iterations of just like identifying things that need to be cycled, applying a commutator that cycles them, remembering that commutator for use in later commutators as a subcommutator, and you know, in like 50 iterations of doing that, or maybe more than 50. I think it's around 50. We start with 318 memorized elements and we end up with 395. So like 80 iterations of doing that and you have a solved puzzle.
Does this code like generalize to like
Yeah.
any twisty puzzle?
Yeah, totally. I have it generalizes to any permutation group. And
cool.
to be clear, it is not. I have not proven it to converge. It does not always converge. However, it involves some random selection of commutators and things like that, and like guess and check type style, type of things. So it's not necessarily going to always work. However, it pretty much always does. I went ahead and made puzzle builder. I went ahead and made a bunch of puzzles to test how it does. And to be clear, like, this is not doing anything fundamentally more clever than what we just did as humans just a moment ago. The only thing that it did that is like slightly more that is different from what we did is it just does a little it just searches more, just does more searching basically. But it's fundamentally still identifying 3 things that need to change, doing identifying the commutator that would change them and performing it, and remembering that commutator for use as a sub element of later commutators. That's all it's doing fundamentally. But anyway, I tried this on
like the ready cube where the commutator doesn't change the corners.
It also knows about conjugates and just naive group element combination. So it would be, it is able to figure that out. It's able to figure out any permutation group, probably, or at least, like, I've tested it on a bunch of them, and by that, I shouldn't say that at all. I have not come up with any rigorous argument for this thing should work in any particular circumstance. However, I sat down, like, when I made it, I came up with a bunch of puzzles to start with that I wanted it to work on, and sure enough, it worked on them all. So the puzzle that I created was this one called a S4 puzzle, so like just for symmetric group of order 4, where I have this idea of a primordial element. By the way, is the text too small? Can you guys see that? Is that better?
Yeah, you can see it.
Oh, yeah.
Okay.
It's better, bigger.
Yeah. Okay. So a primordial element is like a permutation element that is like a single move. The goal of solving the Rubik's Cube is to solve it using moves, right? If I just say I'm going to make a commutator out of like cycling these 3 things that I already that I just select at a whim, like, that's not really solving it, because you have to boil it down to individual moves at the end of the day. So we have these primordial elements, and that is basically like the legal operations of the physical puzzle. So in this puzzle, there are 4 items, 0, 1, 2, and 3, and what they do is one of the operations just swaps the first 2, the next one swaps the first one with the second one, the next one swaps the first one with the third one. So that's one puzzle. Another puzzle is like this rectangular slider. It's like each each line can like do a cycle. So like 4 would come to 0, 0 would go to 1, so on and so forth. Yeah. What's that?
Oh my gosh, you're right. The good reference.
I missed what they said. What happened?
Loop over. It's a
Oh.
puzzle.
What puzzle?
That's what it was
Well-
called. I remembered it came from you, that you made that puzzle. I just forgot the name
Well,
of it.
Well, it's a puzzle that like existed before I made Loop Over, but
Loop over.
Oh, yeah, I mean,
I'm not
I
caught
think
up to
it's
the
like-
lore.
no, it's okay. It was like 2018, so it was like ages ago. But I think it's like a very fun puzzle. Like everything is so symmetrical and like easy to visualize.
Yeah.
Like a 2D Rubik's Cube.
Yeah,
Oh,
yeah.
I've gotten some complaints from people telling me like that's not what a 2D Rubik's Cube would do,
Yeah.
but I think it's close enough.
Yeah, so also I was lazy, so I didn't like add all of the vertical sliding. I just gave it the horizontal sliding and a transpose operation. So if you want to like construct like a vertical slide, you just do the transpose. You make a conjugate using the transpose. So like you transpose, then do the first row slide, and then transpose again, and that is implicitly doing like a leftmost column slide. Does that make sense? Not important. Anyway, that's another puzzle. Yeah.
Well, it is interesting. Like yeah, guys, like that transposing. I feel like that would be harder to implement than like a vertical slide. But I guess it's true. It's identical.
The only reason that it's easier to implement is because I don't have to like write out 5 of these different like lines of like permutation operations. It's just one line,
is there, like,
one
a
line
different-
instead of 5. That's all.
Oh, I get it. Wait,
Yeah.
is it
I was
is
just
there a
lazy.
different operation for like each amount that you shift by?
I just gave it
Oh,
like
no, it's each row.
I gave it everything in its inverse
Right,
as
I get
legal
it now.
operations. Oh yeah. Sorry, I
You
didn't
do the
mention.
inverse. You could just do 4 feet.
You could. However, I forgot to mention this. It does require each primordial element. A requirement of this thing working is that each primordial element has an inverse, because otherwise you can't make commutators in the first place.
Yeah.
So like it is dependent on that constraint. So I wanted to like, I wanted to give it more puzzles that were not like that I wasn't confident that I would be able to solve. So this is literally just a list of 25 items and just 5 completely randomly selected permutations on them. And their inverses. So that's another puzzle that I gave it. Cheese puzzle? Shoot, I don't know where my cheese puzzle is. It's like a little it's just another little puzzle. Like you can cycle all of the things on the top row or the bottom row, and then you can do this sort of like slice operation that'll like flip these with these. This is a physical twisty puzzle that I own. You can Google it online. I think it's called like a Rubik's cheese or something like that. This is another like nonsense puzzle, but this one has 2 moves instead of that one. Thank you. So nonsense puzzle this is just the same thing as the 5 move nonsense puzzle, but this one has 2 moves: 2x2 Rubik's cube, 3x3 Rubik's cube, and one called swap and cycle. This is like you can swap the first 2 elements and you can cycle the entire set of elements. Buffered symmetric group puzzle. I don't remember what this one is. I don't know what this one is.
This would work for a 4-dimensional cube too, right?
It would work for literally any group that can be written in a permutation group, which is every group. Or every finite group, I should say. As long as your primordial elements have inverses. So, okay,
Every
that's...
group is a permutation group. It just might not be a finite permutation.
Yes. Anyway...
Do you have to do?
Sorry, go ahead.
Oh wait, do you have to do anything special for orientation, like?
This is
for the Rubik's
stickers.
Cube?
Yes, yeah, that's a good
it's
point.
stickers. Oh, okay.
These are stickers. I just encoded it with stickers, so that I
see.
don't have to do any of that because lazy.
So, yeah, I was actually thinking about that, and I'm curious if this guess is right or wrong. If we had like a Rubik's cube where like a sticker had a word and we needed it to be in the right like rotation on the sticker, then
Yes.
could you say you're permuting, instead of permuting the, like, all of the little faces of the cubies, could you say you're permuting, like, for each little face, like, the 4 edges of that little square
Yes. Yeah.
are all being permuted, so there's a million things being permuted?
Yes, although that only ever comes to fruition in the centers, because like on the like outlying stickers, like on the edges and corners, like they are mechanically fixed in their orientation.
Yeah.
But
Right,
yes,
exactly.
that's called a picture cube. You can look up like a picture cube. That's like what the name of it is. It's just like a Rubik's cube that has pictures on it. It's fundamentally the same difficulty as a Rubik's cube, plus you have center twists.
I have a picture cube that I haven't really touched in like a decade.
Yeah. There are also nice commutators. I don't know if you know the algorithm. Hold on, let me put my video back on. I don't know if you know the algorithm that'll like swap four centers like this. But if you swap 4 centers, do a face turn, then unswap the 4 centers, like that's your commutator that just kind of solves the problem for you. Make sense?
I have a question about your
Yes.
program. Does it have a way to handle indistinguishable things? Like, I just posted a link, which maybe if you click, will show you. Or here, I copied the picture.
Working on it.
So yeah, so like this puzzle, like all the green balls and all are the same, and all the blue balls are the same.
Yeah.
So there are many valid, like, solution states.
Uh-huh.
Does your program handle that built in, or would you
No,
have
it
to,
doesn't.
like,
Not as is.
Yeah, that's not a group.
That's true. Wait, is that true? Yes. That.
Yeah, like a 4x4 is not a group. You can solve it using a group by pretending that
Right.
all the pieces are already
Ooh.
made, but
I didn't even notice that. That's a good point.
Wait, what do you mean this
any
is not a group?
4x4,
I'm not sure I
5x5
understand.
or up. If you walk,
Like the operations of
Like
Flip?
I think I can. I think I can.
the
Sorry. Go ahead.
I mean, I can do an undo flip, and I can do an undo, like, move the balls around, and I can compose operations. That makes it a group, right?
Well, so I think the problem is if you have the operation that I'm trying to imagine that is very not group like, and I don't immediately know which axiom it violates, is like if you have imagine you have an operation that'll swap the middle 2 elements here, just those middle 2. If that's like an operation you have available, if you do it here, then like the state changes. However, if you do it like when 2 pink ones are in the center, you've done the identity. So you simultaneously have the identity not being the identity.
it violates associativity.
I feel like we must be talking about 2 different things here.
Well, like insofar as you assert that these 4 pink beads are the same beads, like if you are willing to allow them to be different objects, if you're willing to label them, then it becomes a group. But if we're saying that like this state is the same state as when these 2 things are flipped with each other, then you have like positions where the identity, like just going by my proof, Greg Kuber's probably right about associativity problems, but like you can construct an identity that is not an identity.
So basically, there seems to be a way that you, and I guess perhaps the Grey Cuber as well, are using the word group, and I don't understand the context. You're using it to refer to something about, like, identical states in the puzzles in a way that I don't understand. Like, there is a group action on the physical balls.
Mhm.
The group action is all the things you can do with the puzzle.
Yes.
There's a group. So fill in the piece I'm missing.
The piece that you're missing is that two group operations. Like a group operation, there are multiple group operations that do nothing. Under your definition of group
Multiple
operations.
That, like, like the colors in the same spots.
Yeah,
Yeah.
but if it
If they
swaps
want
two
things in
pink,
the same spots,
if it,
sure. But like that doesn't mean it's not a group. It's still a group. I don't get.
it's not, well, it's not a group if you're asserting that two similar looking boards are the same, are arrived at by doing the same group element operation.
Let me rephrase my question, maybe because I'm not being clear, or like we're speaking two different languages, the languages of like twisty or whatever math.
Sure.
So like there is some algebraic object that is not a group that involves these properties of the colors of the balls that I understand. What how do you generate that? Like what is the that object that's not a group that you're talking about?
Um, you could say it's a magma. It might be something else.
No, but like,
But
what are the operations? Like, I understand the group action on the physical objects, but you're talking about the something with some other operate. Like, what's the something? I don't get it.
a magma is something general
No, I
that
know what a magma
like
is.
operate. Okay. Well, I don't understand the question then.
I think I half understand the question, but like the problem is your group. Like I understand the group that you're trying to talk about, but I don't think your group reflects the physical object in front of you, because the the group that you're concerned with is like the physical object doesn't distinguish between these four beads. Your group does, and like insofar as those two things don't agree with each other, you have like conflicts where like you could solve the bead puzzle without like returning to the identity of the group.
So, I'm trying to read the chat because maybe the chat has my. Well, I absolutely agree with what Axiomatic System said in the chat, and then I'm trying to think about cosets of a stabilizer subgroup. Um,
Yeah, I think.
I'm not well. I mean, I don't have to be talking about a permutation representation.
Why not? I
I
mean,
was just
well,
thinking about
like these,
action on the object.
but that's implicitly talking about a permutation group. Like insofar as an action permutes the objects in the puzzle.
Fair, that's fair. So I guess I'll try one more time and then I'll give up so I don't take up too much time. But like
No, you're good.
the Gravekeeper said, like there is something that fails associativity. Like
Yes.
how do we define that something in terms of like the colors and the balls and whatever? Like
So it
there is
like
a magma. What is
you
that
have
magma?
if you assume that you have an operation like A that'll swap two of the same color, and then B that'll swap one of those with a different color, then um, or yeah, let's say that you have I guess it'd be easier to like if you have one, two, three,
I think I'm.
okay,
Mm.
and then if you have like a if you have the setup XXY, then A B A prime is the identity, but then that means that B is the identity, which it's not.
Okay, so when you say is the identity,
Yeah, I don't think the.
you
Sorry, continue.
you're so when you say is the identity, you mean maps on like strings of colors
Yes.
induced by the action. That is no longer a group.
Yes.
Oh,
Yeah,
I
so
mean that's the like object you're talking about. You're talking
Yeah.
about like
if you
what
consider two,
what permutations of colors does the like group action of physical balls, because in physical space the balls are distinct, is like the opposite of the way Two Swap was wording it, but I think you all understand what I mean. Okay, I think I now understand what you're talking about. It would never occur to me to say, that, I have not thought about it in this way. Thank you.
Yeah, I mean, I think that's an important way to think about it though, because like a lot of the time, like as the Gray Cuber mentioned, like this is very relevant in 4x4 solving. Here, let me turn on my camera again. So like, what we were going to do here is like, or the algorithm that I did to swap these two things takes as collateral like some of the centerpieces. It does some operations where it swaps centerpieces around in consequence of doing this. So like the centerpieces here are interchangeable, and you can actually use that to your advantage. You can make algorithms that like under the hood swap these two centerpieces with each other, but you don't care because they're the same color. Does that make sense?
Yeah, I think Jakob Math is speaking my language in the chat. But yeah,
cool, sweet. Okay, where was I? I was gonna show results, but I lost my screen share. Okay, so this is that thing running. Sorry, I'm not good at GNU plot. What this is showing is like this is 3x3 solved with the first two elements in the line of 3. These are like lined up in rows of 3. The first two elements are like sort of greedy strategies where they just kind of naively try to approach the solved state by composing things not invoking any understanding of commutators. So it's sort of like a control group, so to speak. This is like just greedily doing search and kind of applying like composed operations. Whereas the third thing in the row is like using commutators to your advantage, like using knowledge of how the commutator structure can be taken advantage of to arrive at like a specific cycle of 3 known operations. And what you'll see here is like, I think universally on this graph, the third thing in the list always does the best. So like, and like for the 3x3 in the sample that I did, it looks like I think about 90% of the time it was able to find a solution without having like 100 consecutive no-op actions that it like having 100 iterations of not finding a useful commutator. 2x2 it solved it 100% of the time. Like the swap and cycle one, it solved like 90% of the time, so on and so forth. Basically, the smart algorithm solved it, I think, never worse than at a 90% ratio on my like basic simple first test.
Wait, I'm curious. Like, how? So would you like give it a scramble, like a random state scramble, or like?
Yeah.
Well, like, how do you guarantee like? Because half of 3x3 scrambles would be like unsolvable or something like that, right?
Well, no. So it can do conjugates. It can do just basic group operations, but as in like just composition. It's able to just do a single move. So it's not locked into only being able to do commutators, but it is also imbued with knowledge of commutators. That's the special difference here between the one that is doing well and the two that are not doing well.
I think Carrie was asking like, you do a random scramble with the primordial things. You don't do a random permutation, right?
Yes, yeah. I'm not like peeling blue stickers off of the cube and putting them into like the yellow center. Like no weird stuff.
Oh yeah. Oh, that makes sense. Yeah, I guess like given the way that you're encoding the stickers, if you were to just do a random permutation,
that would be.
You would end up with like states where there's like 3 blue stickers on one piece.
Right. Exactly.
Like the odds of like stumbling upon a valid scramble is like, I don't know what it would be, but probably very, very low.
We could do the math. No, okay. I don't want to get too sidetracked, but yeah, you could do the math. That's like 54 factorial over 6 factorial to the sorry,
Oh.
9 factorial to the 6th divided by the actual
yeah,
number
okay.
of positions in the cube, which is like, I don't know, you can work that out.
Yeah, I was worried it was gonna be really hard to calculate, but you could just do 54
Yeah.
factorial, like divided by like 20, that 43 quintillion number.
Yeah.
But yeah, I guess that's kind of off topic.
No, that's on topic. Although I think what's his name? Covoisinage, the guy who does my French channel, he also does, he's a big cuber. He's going to do a talk in here about combinatorics on the Rubik's Cube at some point. I don't know when. So that'll be for
cool.
his
Wait.
talk.
But also, I didn't know you had a French channel. Is it
I
like,
do.
Do you have like?
He has a French channel, really. I just give him permission to post.
Oh, is it like you just send him the visuals and then he voices over
Yeah,
it?
he just does dubs.
Oh,
I also have
that's good.
I also have a Spanish and Indonesian one, and also a Japanese one, but I haven't posted anything on the Japanese one.
That's so
You do your own
multicultural.
dubs on the Indonesian one, right?
Yeah, and on the Spanish one.
Oh yeah. You should learn French so you can do your own French dubs.
Nah, he does a good job. I also like his voice better than mine. I think he has a really, I don't know, he's a good voice. Like, he speaks in French in like this deep accent, and like, holy shit.
Well, I think that like listeners in a different language appreciate when it's like, oh, this is the original creator speaking.
Yeah, that's true.
So I think it's like value. Yeah.
But I'm not gonna go learn French just for that. Maybe I will. I don't know. I don't have that much time though. Okay, anyway. What else did I have here? I have a bunch of things that I forgot what they mean. Mean element impact. I forget what that means. As I said, I made this like a year ago. Mean time taken. Yeah, it took a while to solve the 3x3 reliably. But some of them, it was faster to do the commutator thing than the other like solution methods, because it just found the solution quickly. Did I actually run it for you? I forgot if I actually ran the thing. It's fun to watch. Oops. Wait, what happened? Oh, I did? Did I? I just like watching
like
it.
3 seconds and
Yeah,
something.
there you go. 1 second. So nice. Anyway, that's my show and tell. I did this as a final presentation for a class that I was not enrolled in. But that's a story for another day. Cool.
Yeah. Like, wait, so it runs in 1.1 seconds? Or like, I guess
Yeah.
it probably varies.
Oh yeah. It totally varies depending on the scramble, depending on all sorts of things. You know, if I run it a couple times, it'll probably take 10 seconds one of them. Maybe this is one of those iterations because it's not looking like it's going too fast. Uh-oh.
Right, yeah. Like, some scrambles are just less lucky.
Yeah, and it's not only the scramble. Yeah, so that took 15 seconds. But like something that it also depends on is like it is constructing like a mental map as we do, like when solving twisty puzzles. It is constructing a list of commutators that is already aware of and using those as subcommutators in its further operations. So as a result of that, if it just gets unlucky and like happens to find commutators that don't generalize very well for the first few things that it does, it might get like kind of stuck in a bad place where it's not able to really like continue constructing useful new knowledge. And basically, like on the good solves, what's happening is like usually it finds something that's really generalizable right away, and then it's able to make a new commutator that like also has very small like or very broad applicability, and it just kind of snowballs into being able to continue to nest subcommutators in a way that like it'll be able to basically solve whatever problem you throw at it later on in like the end game, so to speak, in the final stages of solution. I don't know if that made sense.
Oh wait, is it like when you run it one time and then you run it a second time?
Yeah,
it
is rederiving everything each time I run this.
Oh yeah, I was gonna ask like if it's like slowly building up in like a catalog of everything it knows, but like
it does that.
when
It
you
does
run
that. It forgets everything after you run it each time you run it.
Okay, well I guess that's actually good because then that means that like
it figures it out fast. Yeah, and well
it means it's like learning everything from scratch.
Yeah, you can run it. You can run it a second time, and if you do, I don't think I have the code ready to do that. I don't know. I don't know how I would do that. I forget how this code even works in the first place. But if you do that, it like runs really fast on the second run, like because it just knows what to do.
Yeah, like at a certain point, it'll have discovered all the good commutators. And
Exactly.
Just like use
Yep.
that bank.
Exactly. Yeah. Anyway,
Yeah.
that was a fun
yeah,
little
that's pretty
project.
cool.
This is so the point that I'm trying to make is knowing this can really be rather naively extended to kind of just solving Rubik's cubes and any permutation-y puzzles. And we as humans also have like intuition too, which is even a bonus. So the point is you have no excuse to not solve a Rubik's cube. Naifakosi and whoever else has not solved a Rubik's cube.
Yeah, I'll get around to it eventually.
Sweet.
Yeah, I was
Yeah.
gonna say like a lot of tutorials that like people have made to kind of teach beginners how to solve the cube. There will be lots of algorithms they'll teach for the last layer that look very arbitrary. And
Yes.
Like beginners will just be like, oh, this sequence of like 11 moves just does this.
It was handed
like,
down
pattern.
by God
Yeah.
on like
Yeah,
a
handed down
stone
with-
tablet.
Yeah, and what I like about commutators or about like this code that you've written is that like you could logic your way through it.
Yeah, you totally can.
Yeah, and I think that like there was this like thought experiment I saw on Facebook, which was like, if you didn't cube for like 20 years, and then you had to again, like, would you be able to? And I think the memorized algorithms that are arbitrary, you'd forget. But like, if you know the kind of
Right. If you know the philosophy.
mathematical way to do it,
Yeah.
the philosophy, like, I think you still would be able to do it again.
Yeah,
Yeah,
I think so.
yeah. So I think it's probably a better, more robust strategy.
Yeah. It also generalizes. It also like even generalizes to parallel parking. Isn't that cool?
Oh, you mean like if there's like what like 6 cars fighting for like 5?
Did you miss the parallel parking bit?
Oh, I did miss.
Oh
I
no.
was gone. Well, I was searching for my car keys.
Ugh,
It's kind of like
so sad.
went
Here,
to
I'll
the
do it.
depth
I'll
of
do it
the
again. I'll do it again very briefly, but I'm gonna draw the cars very ugly
I
this
just
time.
realized I used a conjugate in one of the programs that I wrote a while ago.
Yeah. It comes up
Not
so
known yet.
often.
Yeah, this program I wrote is a hue reflection. Like, you know the color wheel, like color hues, like 0 degrees would be red.
Mhm.
Yeah, the whole idea of the program is taking an angle on the hue wheel and reflecting all the colors across it.
Okay.
So I
what does
would...
it?
So to do the reflection, the easiest trivial reflection would be reflection across the 0 degree line,
Mhm.
which would just be a
Taking the negative.
360 minus. Yeah.
Yeah.
So to get there, I have to first adjust the color that I'm inputting by the reflection angle.
Yeah.
to
You
align it
twist,
to 0
flip,
degrees.
twist.
Then I do the reflection. Then I undo that alignment to bring it back to,
Yep.
its correct angle. And at the output, it's reflected. Like,
Yeah.
I don't have to deal with a whole bunch of complex angle math. I just have to do a simple
Exactly.
align, flip, realign.
Yeah. Exactly. That's
That's
like
a conjugate.
that's pretty much the exact same thing as I did in when I was, as I mentioned, when I was making that like the slidey, like the rectangle slidey puzzle. Instead of having to go and define like all these like vertical columns, you just do a transpose and then do the thing that you already know how to do and then undo the transpose. Exactly. Yeah. It's a perfect use of conjugate. Okay. So Carrie, the idea is you're here. You're trying to be here. You want to be here in between these two cars. These lines are cars. So you go forward, then you rotate your angle by like 5 degrees this way. Then you move backwards. So X is going forward, Y is turning counterclockwise slightly, X prime is going backwards, then Y prime is twisting your angle slightly. I drew that.
I see.
I drew it over itself because I don't know, but like you go forward,
yeah.
you go forward, you twist, you go backwards, you untwist.
You're
I can see
basically
it.
saying the car ends up in the same state after, but in a different position.
Yeah, it is moved on an axis that isn't one of either X or Y. Oh, that's another great example of where you can use commutators. Although
Yeah, and also like for both of those actions, like driving forward or rotating, if you just did that and the inverse, you would just end up in the same place as normal. Like, which is like
yeah, exactly. Yeah.
Yeah. So it's like the intersection of A and B is like where the
Yeah,
action
okay.
happens.
Yes, I have another great
Oh,
example
yeah.
of this. So, this was something that actually came up at a job, and I can't talk about the details of it, but there's a thing that rotates on a number of axes, and its ability to rotate on one of the axes stopped working. So, um, this
You
was.
can talk about it.
I'm not gonna.
Is this gimbal lock?
Yeah, it's basically gimbal lock. So you have uh, basically you're rotating a sphere, right? And
You're
you
not
can
saying the specific details. You can like, whatever. It's fine if you don't feel comfortable.
I don't want to talk about it.
That's fine.
So you have a sphere, and we now have two axes of rotation of that sphere, but we want to rotate it in the axis that it doesn't have the ability to rotate. Like imagine like we can rotate it in like this up and down direction like this, and this like left and right direction like this. But we want to move it along this axis, right? How do you do it? It's basically the same problem as the parking problem. You can twist the sphere in one axis, twist it in the other, and then untwist it in the first axis. And that'll move where the axis is, the axis of the second rotation. So like if we move this one up, then we can twist along this axis after the thing that it's acting on has changed, and then undo your twist upwards. And that's like the same problem as this. You've moved in an axis that isn't the axis of your quote unquote primordial elements, to use the terminology of my program. So we didn't actually use this as a solution, but I just thought it was a cool example of like theoretical application of a commutator in real life. But that's basically how you solve gimbal lock. Like if you have a gimbal, like a physical gimbal that can't like turn on a third axis, like that's what you have to do.
Are there ever situations where like that works, but it's like not the optimal solution? Like there's maybe like a shorter.
In the real world practical example, it turned out that this just wouldn't be able to do its job fast enough, so that's why we didn't do it.
Okay, yeah. I guess it works well for like twisty puzzles because like you're not like you don't have to operate within like 0.01 seconds. Like you can go slow.
Yeah. Yep.
Yeah, that makes sense. Yeah, it's interesting how often it pops up.
Yeah, it pops up like very everywhere. Keep your eyes out for
another
commutation.
puzzle for you, Alex.
Okay, sweet.
All right,
Playing the
so
first thing is everywhere like
before
Lucas
you
Peppers.
Yeah?
Before you turn your camera off, all right, try this one. Stick your hand out, right? Okay. Now, can you turn your hand over without twisting your wrist?
Turn my hand over. What does that even mean? Like,
Get
what
your
is
palm facing up
twisting
without
meaning-
twisting your wrist.
twisting means this, right?
Yeah. The end state is that you want to have your hand
But
out
like,
in front
is
of
this
you with your
is this
palm
twisting?
facing up.
Is moving about this axis twisting?
No, that's fine. You can do that.
Like, can't I just go all the way back like 180 degrees until it's pointing like up at the ceiling?
So like, basically, like, stay sitting in your chair.
Yeah.
Do not twist your wrist.
Yeah.
But end with your palm face up, like where it is located currently.
Oh, I see. Like, are we saying I like move it like this and then like twist my entire body and then like end up back like here
Okay, so
or something?
You're kind of getting there, yeah.
I mean, I implicitly know the answer to this question, that it's going to be some kind of conjugate or commutator. So like,
Yes.
There must be some more graceful way of doing this than what I'm coming up with though, because like I'm imagining like I move my hand here. Let me adjust my camera here. I move my hand like starting here. Oops, can you see that? Starting here,
Yep,
go like all the way back, like that, and then just twisting my entire body like this until my hand is down here.
Yeah, no, that's you're overcomplicating it.
Okay, what's the pretty way?
All right, put your hand out like you had it to start.
Yeah. Yes.
Move it horizontally towards your chest. So like bring it horizontally towards your chest.
Out. Okay, horizontally. Horizontally meaning like this?
Yep, exactly. Now bring it vertical.
Like this.
Yes. Put it down in front of you. So extend it in front of you again. Bring it back towards your chest.
Like this.
Bring
Okay.
it
Yeah,
up,
yeah.
bring it down.
I
There
see.
you
I see. Yeah. And then I could keep rotating indefinitely in theory.
Yeah, sure.
No.
You try that.
Yeah.
I had a question before we go about basically how much terminology is standard and how much terminology was like just for this talk. So I have interference or buffer for
buffer.
the intersection of the
Buffer is a kind of specific technical word in the context of blind solving. Like.
So it does not mean intersection of the two operations X and Y.
Does it? Hold on, let me think about that. I think it. No, I don't think it does. It's kind of a different context, and don't. I tried to correct myself every time I said it because no, that's not the same thing.
What about setup move?
Setup move is a very common term in cubing. That is a word.
Okay. What about to swap instead of transposition?
I don't know if that's a me thing or if that's a general term. I think I've heard it. I think people say that.
To cycle, but I've never heard to swap and swap, but I've never heard to swap to mean a transposition.
I think I've heard it.
I was gonna say, like, I have the what's the word? Like, I have this habit of trying to use cubing terms in non-cubing videos, like free cycle or like odd parity, and I just realized like, oh, I don't actually know if that's like common knowledge or not. Like, I don't know.
Those are also just math terms.
Yeah.
Oh, that's good. That's good.
Well, so the thing is, they're not all math terms. That's why I'm asking. Like,
right.
Cycle is a math term, but setup move is not a math term. Conjugation is a math term.
Right.
Oh. Okay.
Yeah.
And then like, but I was gonna say like, is prime a standard?
Prime is very common cubing term. Some people will say inverse. Some people will say prime. I usually say prime just because one syllable.
Is like standard in math.
Yep.
But prime might not be understood.
I'm currently in calculus. So every time I hear prime, I just think derivative.
Yeah.
That too,
like f prime.
Yes, it's also notated with an apostrophe usually in context of cubing.
Okay, and what about primordial element?
That is me. That is not even cubing. That I made that up. That was my program terminology. Like I don't think that's a thing to describe like what this element of the cube group is. Like I made that up.
I mean, it's either like it seems to be a generator.
Yeah, it's a generator. Yeah.
And I guess I'm pretty sure this is standard in Twisty Puzzles, but just writing the group product in like the order, like from left.
Yeah. Actions are read left to right in algorithmic notation.
Okay.
Wait, is it right to left
in group
I
theory?
remember, like in group theory, it's right to left.
Think of it as like function composition. Like R is like
function composition.
Yeah.
Actually, it's worse. It's right to left in most books, but there are books that do left to right for like when they're doing a lot of calculations with big products. I think there are a few math books that do it in the other direction.
Well, maybe like they're trying to change the standard, but like it's really hard to change something that's like cemented in.
I don't think the standard's bad though. I don't think it's like right composition. I think makes sense because like you are.
Makes sense.
Yeah, cause like if you imagine putting the like think of the thing that think of the group element that we're talking about as a function, right? That changes the cube, or it's a function that changes some other group element, right? You would write that thing before the thing that it's changing because the thing that you did is a function, right? So like if like this move is f, you would say f of x, and x is the thing that you do before it, right? Because it's acting on some position.
Yeah. So
Yeah.
And so what I was getting at is there's if you're doing like homological algebra or something like that, you have a lot of compositions of functions, and so you don't write circles between your functions, so it looks like a product.
Mm-hmm.
And then like some of those books choose to say, all right, I'm just going to go in the other orders. I don't have like if they had composition circles, they'd be forced to follow rules for function composition.
Right.
But they're like, no, I just want to go left to right.
Yeah. Yeah, no, and
Well, I imagine yeah.
Sorry, go ahead.
Like it becomes a problem if like one book
Yeah.
uses two systems within itself. Like, that would be the worst.
I think left to right. Personally, in my brain, everything is left to right, but that's only because I learned cubing before I learned anything about math.
Yeah, I think it's like if I draw in the parentheses of like f of g of h of x, like it makes total sense.
Right.
But yeah, with cubing, it's like I think you're kind of just it's like because they teach these to like 8-year-olds, and it's like, oh, like just do this and this and this and this. Like I think
Yeah, it's a sequence of
kids
actions.
absorb. Yeah, sequence of actions.
Yeah, they read right, like left to right. Yeah, so.
Yeah, I think cubing is interesting because like there are like college professors who are like interested in the math of cubing, but then there's also like 7-year-olds getting world records, and they both use the same like terminology.
Yeah.
So it's like this weird overlap of like it has to have kids understand it, but also we're talking about like group theory. So I don't know. I think that's one of the reasons I like cubing.
Yeah.
Yeah, and I already knew this one, but I was very confused when I first saw like algorithm being used for like sequence of operations and not what I would have called an algorithm before I.
Yeah. You would think that the whole solution to the cube is the thing called the algorithm because it's like a sequence of like if-then statements, but algorithm means sequence of moves. It just means a group element.
Oh yeah. I guess like algorithms like in computer science like Dijkstra's algorithm. It's
Right.
like a
Is
like,
a method
yeah,
in
a
cubing.
method.
Yeah. Beginner's
like,
method
it's
is like an algorithm in the mathy language.
Yeah, I always wonder with these things like how it came to be. Like maybe it's just one person on some forum in like 2004 decided to name it that, and like because people just kind of copy what came before, it got like more and more cemented. Like I could see an alternate universe where cubers never called them algorithms, and they just said like, oh, these are my sequences or something.
Yeah, totally.
But yeah, I guess we're stuck with algs.
Yep. It makes sense in my head though, so I'm not complaining. But I'm just used to it.
Yeah. I'm used to it too. Yeah, I've been cubing since 2013, so I feel like that seems to predate a lot of other stuff in my head.
Yeah. Cool. Any other
cool.
questions or anything? Thanks for coming.
Yeah,
everybody.
well, I was very curious, like,
I got nothing.
what these sort of events were like. So I didn't know until today. Yeah,
Well, this
it
is
was fun.
This is the third one. The third one and the second one that I've given. So, but there will be more. So hop in.
Yeah, that's good. Yeah, but yeah, like I remember, like you were saying, like, oh, it's a departure from kind of the polished video where you like script it and then like it's maybe 10 minutes of like.
Yeah, to be clear, this is not going on my main channel. I'm gonna post these on some dark and like dusty corner of the internet. I don't know where.
Oh yeah, that makes sense. Like I think it should be separated because like
Yeah.
it's a very different medium.
Yeah.
I know like one video I reference a lot is like Matt Parker stand-up maths on YouTube.
Yeah.
He has a second channel where he does a similar thing where he would just post like unedited hour-long videos of him talking about math.
Uh-huh.
And one video was him like analyzing so he had a Christmas tree, and you could write code to change like what lights would light up. So he let
Oh,
his
yeah, I've seen
fan.
that one.
Yeah, yeah, no, he let his
That was
fan
so
submit
good.
code, and it's just like an hour of like no editing, but like that
Yeah,
video blew
yeah,
up, and it's like I was just like, wow, if I don't have to edit my videos and like you can get like 10
Oh,
million
yeah,
views,
that's the one.
maybe that's the strat.
Wow.
Oh yeah, that's the one. That's the one. Oh my gosh.
No, yeah, D arrows. I run untested viewer submitted code on my 500 LED Christmas tree.
Yeah. We all
Yeah,
should
that's
do
great.
that.
Yeah, I think one thing that I've sort of intentionally or unintentionally hacked on my channel is, I one thing that I think that works quite well is just having a high information bandwidth, like in the sense that just like lots of information all at once, whether it's visual or narrative or otherwise. Like that's why people watch TikTok, is because it's just fast. You get a lot of information quick, right? And I think my videos are
Right.
visually like that. But I'm not doing the animation, right? I just hijack math to do it for me. So I think that is,
Working.
yeah, I think that's I didn't realize it at the time, but I think that's a total cheat code that I've activated. And maybe like I think this is kind of an example of the same thing of like, he's just getting other people to generate the content for him live, That's the way you got to
Oh
do
yeah.
it.
Well, I would consider like if you have to write code to have something appear on the screen like describing some math phenomenon, like I would consider that like even more work than animating in some ways, because like I don't know, like for me,
Yeah, but
when I
like
do
yeah,
something
but like
that's like a lot of debugging.
yes, yeah, but like per visual effect, like there's no way I'm going to go and draw a whole Mandelbrot set or a whole like I don't know what, like any fractal. Like you can't do that. You can't animate that by hand.
Oh, that's true. Yeah,
Yeah.
like the math kind of like speaks for itself, and you're just kind of here to be the messenger for it.
Right. That's what I mean. I'm talking in the context of like fractals and stuff. Like when it's just some kind of visual effect that I didn't like explicitly tell the computer how to do. Just only by means of some mathematical construction.
Yeah, it's just sort of emerged. But yeah, I agree with like that point that like TikTok is really fast, because I will say, there are like unedited videos that I'll make or other people will make that are like 2 hours long, and like when I watch them, I do think like I can't sit through this. Like this is too much time. Like I do think we should appreciate and respect the people who like edit their videos down.
Oh yeah.
Because it's like way easier to digest.
Yeah.
And higher digestibility also usually leads to better understanding of the topic.
Oh
yeah,
like
definitely.
every sentence that's said is like kind of
more
constructed.
dense.
Yeah, dense and like takes you down the right path to like the insight.
Right.
Whereas like a lecture, there might be filler sentences that cloud everything.
Full primers and guiding paths.
Yep.
Yeah, exactly. Yeah. Well, yeah, I know there's a channel called Primer, but that's a different subject.
Yeah. Great channel.
Yeah, I agree. Evolution simulators, yay.
Yeah. You probably inspired them.
Yeah, I can never get enough of that.
Oh yeah, well I met him at VidCon once, so I was like, because I didn't know what he looked like.
Nice.
So he had to come up to me and say, "I'm Primer," and then I was like, "Oh, like that's your voice sounds familiar now." But like, I think other than VidCon and stuff, it's hard to meet educational creators, which is why I'm glad we're doing this right now.
Yeah.
But yeah, I think Primer's videos are very definitely like scripted and like edited, and there's every second is used to its most, to its fullest.
Yep.
Yeah. But yeah, thanks for hosting this too, Flop.
Hell yeah. These will be probably happening every couple of days, so stop by.
This is really fun.
Sweet.
Yeah,
Glad you liked it.
Yeah. I will be back.
Awesome.
We'll see when, but I'll definitely be back when another interesting topic arises.
Beautiful.
All the topics that Carrie does not attend, not interesting. So.
Not interesting. Yeah.
Well, that's cool. Well, I will say there were some college classes I took that were like way too abstract for me. Like I don't know. I think that like college math was like I loved like high school math, and like so some of it got like really theoretical, and then I was like, whoa. So I think that's kind of why I did CS instead. But
yeah. I'm
But,
hoping to
okay.
keep these like not specialist friendly. Um, although we'll probably have a mix of
Yeah.
everything. There'll probably be some videos that are like, I think one of the guys is going to give a talk on like how does a car work. So we'll have stuff like that, but like also
Oh, cool,
probably
yeah.
some deep math too.
Yeah, I might do one on CPU architecture because it's like my whole thing.
Yeah.
Oh, cool. Yeah. No, I think
Yeah,
like
I've made like I just have a folder here and it's just full of tens of iterations of designs of CPUs.
oh wow. Yeah, I always feel like I'm super on the software side of things, so hardware is like every time I see it, it's like it kind of like activates my brain in a different way. Like,
yeah.
There are a ton of parallels actually. Like instead of variables, you have hardware registers. They can't store anything but a number, but that number can represent anything.
Oh yeah, well, I remember like I had to take a class in college that was like teaching assembly and like on Raspberry Pis or something. And
Yeah,
I just remember
it's really close to bare metal. Like it's literally just one step above, just directly writing binary into the code.
yeah, I remember like the concept that like really blew my mind was like they were saying like, oh, this isn't like 0 and 1. We're talking about low voltage and high voltage.
Yeah.
And I just thought like, oh,
Yeah,
so you
and
mean like
anything that has two states, it can be binary. It can be a computer.
yeah. But I just thought like, oh, while this operation is happening, if I like zap it with lightning right now, it would work, would it? And they said
Yep.
like, no,
Yeah.
it would
No.
not.
Yeah.
There have been
Yeah.
videos made about the cosmic rays,
Single event effects. Yeah.
flipping bits.
Yeah.
Yeah, like, that's the real world is messy.
Yep. That's whenever my code doesn't work, I just blame it on like high energy ions from space. It wasn't the code's fault.
Yeah, so I think based on what you're saying, Tishraf, I might, once I figure out when I can give a talk, I'll probably try and poll for like, what background do you have in math, and like, to tailor something.
Sweet.
based on that.
That would be appreciated. I also don't want to give the impression that you have to tailor anything at all. I think part of what I'm trying to go for here is that it's low effort for the presenter. So don't worry too much about it. But
Right, but like,
do whatever you
I don't
want.
want to give a talk that no one could follow.
Yeah, sure. Well,
Yeah, I'll probably be teaching for first. I might have to do two. For a first talk, teaching building up a simple CPU from components, and a second one doing algorithms on a simple CPU on that CPU that was built up. That'd be fun.
that'll be fun.
Yeah, I think that'd be cool. Like, I think having kind of the like foundation set by the first one makes it easier for the second one, because then you don't have to like constantly ask like, wait, do you know this concept? Like you can already just assume that people know it.
Yeah.
Yep.
And it is one of the coolest parts about learning it for me was like just seeing how it goes from just the wires and the gates to components to just putting it together into a functional computer.
Yeah.
Like, you know what each thing does, you know what all the little bits do, but after putting them together, and it's like, it's almost magic, but you understand all of it.
Yeah.
Yeah, it is kind of magic. There was a viral video recently that's someone teaching you how to make a CPU from rocks, but it's only 1 minute long.
Oh, I think I saw that. Yeah.
Which is why, like, I think
Too short.
that's part of the joke. It's like, this isn't enough time to teach all of human history.
Yeah.
You know, we
Alex,
managed to
what do you
trick
think
rocks into
about-
thinking.
What do you think about more open-ended topics? Like, do you remember working on the prime sum problem?
Yeah, that's
We never
that's
actually,
totally
like,
fine.
solved that, but I wonder if that would be an interesting one to kind of like have
Absolutely. I think
as a
that's
group
perfect.
present it.
The every even number is the sum of two primes.
No, this is different. So there's think it's a number file video out there, but basically, you can take any string of integers. I might be misstating it. I'd have to go back and look at it.
I don't remember
And
either.
arrange them such that the consecutive integers sum to like prime numbers or something like that. And so what me and Two Swab looked at one day, we had math club at work, and so we would sometimes look at these problems, and we were trying to see is that same thing can that hold true for prime numbers instead of squares, and we were making good progress. I think where we ended up was that you were pretty well convinced that it was true, but we hadn't proven it yet. And I was still a little bit doubtful because of primes getting sparser as they get larger, but then again, like, so do squares, and so I don't know what to think.
Yeah.
Anyway, I could present it sometime.
Do it. I'm so in.
Yeah.
Wait, also, wait, Haugen Mitch, are you the friend that like was solving the Klotsky puzzle in the video? Because I just remember like you felt it's like, oh, my friend was trying to solve it till 11 p.m.
That's
No, I do not have that same level of patience. That was another friend of ours named Victor.
Oh,
but
okay.
yes,
Oh, cool.
Wow, good memory. Good memory.
yeah.
Wait, this is good. I'm starting to understand the lore. Like Victor now. Now I have to go meet Victor. Like connect all the dots.
Ooh, I'll get Victor in here.
He
I don't know if he has
he's a cool
Discord,
guy.
but he would probably join. He could give lots of math talks but not on math, probably on physics. He's a quantum guy.
Right, right.
Oh,
Physics
interesting.
is
Yeah.
deeply intertwined with math, after all.
It's the same thing.
Yeah.
Pretty much.
Yeah, and if he could give a talk on Klotsky now that he solved it.
Yeah, yeah. All right. Well, thank you all for
Yeah.
coming.
Yeah.
I appreciate
Yeah,
it.
yeah. Thanks for hosting.
talk.
I'll
Absolutely.
see you soon.
Yeah.
I'll figure
Alright,
out
bye,
how to solve
everyone.
Rubik's Cube again.
Bye bye.
Oh yeah. Bye.
Bye.